There it is. All right, so let's take a look at this 1987B. So you should be checking your answers on that, hopefully. One thing that they do want on the AP test is they want you to show your work. So even though we've done this like method up here or whatnot, you probably want to go ahead and write out for full credit on these is like which the rate of the reaction that you're doing divided by the second trial that you're using, and then basically writing that work out. And what you should find out for this is that it is first order for mercury 2 chloride and second order for the oxalate ion. And if you have questions, by all means, just speak up. On the basis of the rate law determined in part A, calculate the specific rate constant, specify the units. So basically you could go with any of these that you wanted to, trial 1, 2, or 3. Obviously you can't go with trial 4 because you don't know that yet. But using trial 1, 2, and 3, I use trial 1. You rearrange the rate law equation to solve for K. So we divide the rate by that and that squared. And then if we take a look for the rate law here, the rate we have, it is molarity per minute. And down here we have molarity times molarity squared. So that's going to give us basically this molarity is going to cancel out with the molarity on top. It's still going to be minutes to the negative first, and we have molarity squared on bottom. So the units for that would be m to the negative second times minutes to the negative first. C, I believe we did C in class yesterday. Yep. Basically, it reminds you that as these are decreasing, these are increasing. So the initial rate of formation for the Cl is twice as much as the initial rate of disappearance for the oxalate ion. If they had asked for the mercury dichloride or mercury 2 chloride, then you would have basically made that a 1-to-1. This appears at the same rate or forms at the same rate that this appears. This disappears. A D, calculate the initial oxalate ion concentration for experiment 4. So basically you rearrange this rate equation up here to solve for that oxalate. So if we take a look here, we have x squared. So we divide both sides by K and 0.316. That's to the first because it's first order. And that gives us x squared equals that. If we take the square root of the whole thing, then that gets rid of our square there. Doesn't look like I actually put that in there, I guess. Take a look. Square root. .264. So we get 0.514 for the concentration of the C2O4 -2, the oxalate ion. It is a concentration, so we should have moles per liter on there. The other problem we were to do is 1980D. So with this, it gives us a reversible reaction, X yielding A plus B, or the reverse A plus B yielding X. You talked about reversible reactions in the first year chemistry course, whether you were in X or CP. Basically, reactions reach equilibrium, and that's what this system is showing. Another thing that I'm not sure that we've talked about directly is that delta H of the reaction here is positive. So that means that this is adding energy, or is what we would call endothermic. That's actually our next unit, is the thermal chemistry. So that will become more apparent as we go through it. It says the forward reaction is a slow at room temperature, but becomes rapid when a catalyst is added. Draw a diagram of potential energy versus the reaction coordinate. So this is going to be another one of your, basically just drawing that progress of reaction to potential energy. It says for the uncatalyzed reaction on this, label the axis. We got that. The energies of the reactants and products. So here is the energy of the reactants. We could put X there. Or we could put the H of X. Now, if we have that, this is endothermic. So what do I need to do with my line for my products?
It has more energy.
Has more energy. It's gaining, right? So we need to put that up here somewhere. And then we can, you know, put the H sub A plus B. Now we just basically connect it because it does want the energy of the activated complex. We need to connect that with some type of curve. And here we have the activated complex, also called the transition state or whatever. Now they say that they want the one of the uncatalyzed reaction. This is different than like a multiple choice one, so we probably should put up here uncatalyzed or something like that so that they know what we're doing here. And then it says all significant energy differences. So here is that delta H. And here is our activation energy. I guess you could do also, this would be the activation energy of the reverse reaction. Let's put this of the reverse. Yeah, I think that'd be good. So the next, it says, on the same diagram, indicate the change or changes that result from the addition of the catalyst. Explain the role of the catalyst. So basically here, we would start to do some type of dotted line. Again, this is a generic diagram. We don't need, you know, certain amounts or anything like that. And then we would sit there and explain the role of the catalyst. Actually, it doesn't ask us to, I'll go ahead and put it here. This would now be the activation energy of the catalyzed. And notice that the delta H does not change for this. That's very important. The delta H does not change for that. What is the importance of the catalyst? Basically, it creates an alternate pathway, right? B. Way with a lower activation energy. So what that means that if we were to look at the Boltzmann curve or whatnot, more of the reactants would have that energy required, that activation energy required already, because they don't have to get over this bigger hump. If the temperature is increased, will the ratio of the K of forward or the K of R increase, remain the same, or decrease? So basically it's asking how does K of forward or the rate of the forward reaction, the K of the forward reaction rate, compared to the rate of the reverse reaction. Justify your answer with 1 or 2 sentence explanation. So if we take a look, what's we are increasing temperature. So an increase in temperature that's going to favor or increase the K of F over K of R. Anybody want to tell me why it's going to increase it if we increase the temperature?
Adding more heat to an endothermic reaction will speed up the reaction faster than it would an exothermic reaction.
You got it. Because the forward reaction is endothermic. Now, if that one was, if it makes sense now, obviously, it may have been a problem with recollection of equilibrium from last semester and what's called Le Chatelier's principle. But think about it this way. If we have this as an endothermic reaction, we add heat. Basically, that's going to make the forward reaction go faster. The reaction rate of the forward reaction is going to be faster. All right. All right, then let's take a look at what's called the integrated rate laws. Now, let me show you guys how these are given to you on. We're going to go a little bit more in depth in this than the AP requires, but if we take a look here, this is the AP equations and constants sheet. So when it comes to the kinetics, these are the only things that they give you. That's a little, I think that can be better focused. It may actually be because of the height of here. Okay, cool. So basically here you have the first order. And this is the second order integrated rate laws. A of F stands for final concentration. A of naught stands for initial concentration. We know what K is, and T is time. So what these allow you to do is, if you know what K is, and you know how much time has passed, then these will allow you to, if you have the initial starting concentration, or you can find the final concentration after that much time has passed. I'm sure that you can imagine why this might be important, because you can sit there and say, okay, how long will it take me to change the concentration of this to this, right? This is if it's in a second order reaction. And we're dealing with only one, basically only one thing here. So this would be like a decomposition reaction or something like that. We're only dealing with one reactant. So if it's a second order, you can see that it is a little bit different of an equation. Basically because the way that we're making these is we're taking the old change in concentration over change in time equal to rate times K. I'm sorry, I messed this up. This is the rate, one way to look at the rate law. And I tried to make this into rate equals K. But this is K times whatever this is to that order. Well, when you set these equal to each other, you need to make what's called basically the integrated rate law. And those two are given to you. Here's the integrated rate law for a zero order reaction. So we have the concentration final equals negative K times T plus the initial concentration. Now, if we take a look here, we know that for zero order, rate equals K times the concentration to the zero. Well, in reality then, that just means that rate equals K, right? So if we take a look, remember we're dealing with the concentrations of the reactant. So that means that as time goes on, the concentration of the reactant goes down. For a zero order, then what we're going to end up getting is basically a slope going down this way. So the way that this is set up is, if we take a look here, we have this in basically we have negative the slope times time plus the y-intercept. So what your concentration is going to basically be is multiply the negative. So if we take a look here, the slope will be what we call negative K. And your concentration of final will be the time times the negative K minus that y-intercept. That will basically give, you know, and this is kind of cool because instead of telling you that it's zero order, they may tell you that, well, we've got this graph by plotting the concentration to time. Or they may tell you, well, the slope is negative, and it's, you know, it's linear for the concentration versus time. For forced order,
Concentration decrease over time? Like
for the
within the-
reactants, yep. If we look at this, this is the reactant for sure. So if we take a look here, first order reactions, it's kind of the same setup, except for because we have that power of 1 here, we can't really necessarily do that. So if you integrate the change in concentration of the change in time with the Ka to the first, you get this guy right here. Now, if we take a look, we know that we can change from the natural log of A to divided by A naught to the natural log of A minus the natural log of A naught equals negative KT. Well, then we can actually change this to the slope intercept form by doing basically adding the natural log of A naught to both sides. So that would give us the actual equation that they give you on the reaction, the equation sheet, the formula sheet. We're adding that to both sides. So again, this would be our slope, time would be our x, and this would be our y-intercept. The problem here is that instead of using concentration of A, we actually have to use the natural log of A. To time, well, not much different because we're going to get the same type of graph, but this time with the natural log. So what they will do is they may sit there and I'm trying to think if we have an equation that actually says it, but what they may do is they may say, okay, by taking the natural log of the concentration of A and comparing that to time, we get a linear graph and the slope is negative. And basically, there's several ways that they can tell you what the order is, just besides giving you the order. They can give you the K, and they can show you the units for it. They could give you the graph. And that would tell you that if it's concentration to time, then that is a 0 order graph. Or they may give you, okay, this is, you know, if we take a graph of concentration of A for first order to time, we're going to get something like this. So if they sit there and they say, okay, for the concentration of A at a time, it looks like this. For the natural log of the concentration of A at a time, it looks like this. By looking at these two things, well, you know it's not 0 order because it would look like this. And, you know, they show you this or whatnot, so it must be first order. So that means you would be able to use this equation to work that through. Which version of this is actually the version of that they give you on the form. Okay, they actually give you this version on the form. I just showed you how to do it to the slope intercept. So if we take a look here, again, for some reason I couldn't adjust these graphics to put that final there. So if you want to put that on there, I mean, in reality, this could be at any time. Do you know that this is the initial starting point? For second order, if we take a look, here is our equation. So if we were to change this, we get A to the final equals, now notice for this, the K is positive. Keep in mind that we are squaring the concentration and we want to add the naught. So this time, if we were to take the concentration of A at a time, we would get something similar to that. But if we take the inverse of the concentration of A to time, this is the only one that has a positive slope. So K is positive, and remember that equals the slope. Mx B and Y. So again, this is the formula in slope-intercept form. And basically what they're doing here is they're showing you that they can actually graph the data out and you can determine the order for something. If you were plotted, if you're given a bunch of concentrations and times, you could sit there and plot that graph. If you don't get this, you know it's not 0 order. Then you could sit there and add another column and then take the natural log of the concentration and plot that graph. If you don't get this, then you know it's not first order. And then you could plot the inverse of the concentration, and you should get this if it is second order only. Questions there? All right. So half-life. Half-life is basically the amount of time, and I'm sure that in biology and stuff like that, maybe even physics, you guys have covered this, but half-life is the amount of time required for 1/2 of the reactants to disappear. Now, for radioactive decay, all of those radioactive decays, those are second orders. Let's just put that radioactive decay. I'm sorry, first order. I was thinking of half-life and for some reason thought of a 2. But all of those are first order. So knowing the half-life is the time it takes for 1/2 of the sample to disappear, we get the following relationship. So for first order reactions, basically you get the half-life is equal to the initial concentration divided by 2 times K. And what this means is that the half-life is basically, it's directly proportional to the K and indirectly proportional to the concentration. So if we look at those two things, the concentration and the K are dependent on the half-life, or the half-life dependent on those two things. Now, for a first order reaction, they are not. It is only dependent on the K. And that's because you basically have this, the natural log of 1/2 equals negative K T 1/2, and 0.693 is the natural log of 2, I believe, or is it e to the second? Yeah, the natural log of 2. So if we take a look here, that tells us that for first order reaction, it does not matter what the concentration of the sample that you had to begin with is. You just basically 0.693 divided by the K, the rate constant, and that will give you the half-life. And the only difference, and again, these are all based off of these integrated rate laws. So again, if we take a look here, we're dealing with the reciprocal again. So instead of the concentration of A being up top for second order, we're dealing with it down on the bottom. Again, the only one that does not is the half-life that is not based off of the concentration is that of the first order. Maybe I should write that here because that makes more sense to have the radioactive decay right here. Radioactive decay. Radioactive decay. All right, where are we at? 20 minutes-ish. All right, so let's say we have the initial concentration of the reactant is 0.75. So what is that? That is our A naught. And it is used up in a zero order reaction. The rate constant K is 0.015. So there's our K. What will be the concentration of the reactant after 15 minutes? So there's our T. So if we take a look, one thing that you want to make sure happens is that your minutes, your time unit is equal to your K unit. Otherwise, if this were molarity per second, we would have to change this to seconds as well. So we have initial concentration, we have K, we have time. So we're going to go with the integrated rate law here. Concentration of A naught equals negative KT plus concentration of, concentration of A final equals negative KT plus the concentration of A initial. And basically, we would just plug these in. Boom, boom, boom. How long will it take the concentration to be reduced? To 0.06 molar. So then instead what we would do is we would have to then to rearrange this equation. We have the K, we want the time. So to rearrange this equation, we will take and subtract A naught from both sides. And then to isolate the T, we will divide this by negative K. And that's basically what all of these problems are doing, is they're having you do the rearrangement of these equations. One that I do want to do with you, is definitely this half-life down here. Again, you can see that the AP test does give you this half-life equation. So they're going to be more focused on radioactive decay or something in the first order. But they will want you to be able to find concentrations or find the amount of time that goes by from going from a certain concentration to another concentration. in both the first order and the second order. And they don't seem to care that much about the zero order, but that may change, right? So if we take a look here, the half-life of iodine 131 is 8 days. How long will it take iodine 131 to decay by 87.5%? So for that, we could do the, this is actually kind of cool because remember, it is only dependent on K. One quick way to do this is to find out if we have 100 grams in 8 days, how much is going to be left? Anybody? 50 grams, right? And then in another 8 days, how much will be left?
25.
25. And then in another 8 days, how much will be left?
12 and a half.
12 and a half. So right there, we could find out how much to decay 87.5 by basically just doing the half-life. That's also the cool thing about if we take concentration to time, and we are looking at something that's in first order, they may give you a graph like this, and you'll be able to sit there and look at whenever this is, let's say this is 1 to 5, and then you'll be able to mark that. And then whenever it's 2.5 or whatever, you'll be able to actually see that that does stay constant with that time. And the other way we could do this is we could solve for K. Divided by the 8 days. And then we could plug that K into our equation. Let me see real quick here. So then we could plug that K into, we have the initial and final because they tell us basically we are at 87.5%. So it is decaying. So you could start with, just like we did, 100, or you could start with 1, and then your final would be 12.5. Or I'm sorry, if you started with 1, it would be 0.125. And basically plug that into this guy right here. Actually, let's do this. So if we take a look here, that this is the better one. Over, this is the final, over the initial. And then that would be equal to negative KT. And then what we would do is basically divide both sides by negative K. So we have 1 up here. I'm sorry, we have 0.125 here and 1 here. Find the natural log of that, divide it by the negative of whatever we get here, and that will give us our 1, 2, 3, our 24 days. All right, so if you want, open up to page 19. This is kind of a quick summary of what we talked about today. Basically, it gets you to that line equation, and it shows you where everything is, and then the second order as well. And it gives you a graphical representation like I drew. If the concentration to time gives you a straight line, negative slope, then you know it's 0 order. And if the natural log gets you that, and it's to time, then you know that it is first order. And then if you have the inverse to time, gives you, this is the only one that actually has a positive slope. And they say basically remember that k itself is the absolute value of the slope. It is the formulas and stuff like that where you have the negative k and stuff like that. So keep that in mind. But here's a little reminder for you. Concentration, natural log, reciprocal. Keep it clear. Concentration is 0 order. It's just the concentration of time. The natural log is first order, and the reciprocal is second order. I think that's all I wanted to get through today. And we actually, I think, got through some of the second order stuff. Let's see here. You don't have D yet on that. Did that one? Okay. Here we go. So the measure of a rate of reaction is its half-life. One method of determining half-life of a first order reaction is to plot certain appropriate data. Sketch a graph that illustrates the application of such a method. Label each axis with its name and appropriate units and show how half-life can be obtained from a graph. So with this is kind of a trick question because they're asking you a graph about something that's first order reaction, right? The easiest way of this would be to just log the, or to have the concentration compared to time. Because if you know the concentration, if we say that this is 1, this is 5, this is, I'm sorry, this is 10, this is 5, this is 2.5, so on and so forth. Basically, we can sit here and find out the time it took for that to occur. And then make sure again that we check this one to make sure that these two things equal each other. That's how you know it's first order reaction, because it is not dependent on concentration. It's only dependent on the K. So for first order reaction, that would be true. The amount of time it took for that to become half and then half again, these times would be equal. And that would be your half-life. Label each action with the name and appropriate units. We can do seconds here. In concentration, we can do just molarity. Amount of time for 1/2 the substance to decay. And this is the amount of time for 1/2 the substance to decay again. Done. Don't have the ability to do that. We're running out. Okay. The last page of this is a summary of all of these type of things. If you take a look, here is the regular or instantaneous rate loss. And then they have the integrated rate laws, which allows you to go from the initial concentration to another concentration over a given amount of time. And then here are the linear forms. So you have your y-intercepts and your y and your slope. And then they tell you what are on the axes for these graphs and what those graphs will look like. And there's the half-lives too. Nice. For tomorrow, let's go ahead and do 1981B. I think that'll be it. And then what I'm trying to do, one of the things I'm having issues with is finding examples. Fortunately, there's not, I don't have any files for Mr. Verbrugge that have like some examples to do some of these. So if you're worried about rearranging these equations or whatnot, I will post the answers to these tomorrow if you want to work through that. Don't forget, if you want to get the math behind how that rate law was integrated, let me show you real quick. Right here, you're more than welcome to go through that. Here's all the calculus behind the zero order, the first order, and the second order. But that is not a requirement for you for this course. The good thing about these videos, though, also is after they show you how to do that, he will work actually the problems that we have here as well if you need extra time with that. And I think he actually does the, is that where, yeah, he does the actual breakdown of it in the end. That's all I got for today. If you have any questions, by all means, stick around. Otherwise, do that one problem. And I'll see you guys tomorrow.
Thank you.
Thank you.
Thank you.
Thank you. Have a good day.
You too. 1981B. Man, they jumped, huh? All right. Alexa, shuffle my playlist school songs.
Shuffling your playlist.